Welcome to the 1800s. Australia is in a gold rush frenzy, and you have excitedly found yourself your very own one-dimensional patch of land. You can move along this patch and perform an operation. Dig all the way down to see how much gold is in a particular spot. We can model the amount of gold in this land patch with a function, say f of x. But there's no way of knowing the value of f of x without digging a hole. Your family needs money, and you must find the maximum of f of x so you can dig up all the gold in this patch. But it is only a matter of time before other people find this patch of land, so you have to work fast. Well, where do we start? Just randomly digging in spots will be too slow, so we need some sort of methodology. Let's instead try to formulate this problem a bit more mathematically and see what we can come up with. First, we wish to optimize f of x on a bounded domain, and we want a global maximum, not a local one. 2. We know nothing about f. It can be any shape, so things like convex optimization don't work here. 3. We can't perform derivative calculation, so gradient descent is off the table as well. 4. The only thing we can do is evaluate f of x, but this is expensive, time-wise, so we had to be smart with how often we do this. So how do we solve this? We use a technique called Bayesian Optimization. Wow. But wait, what's that? Bayesian optimization works by creating a prior distribution over all functions that f could be. Instead of trying to draw out all infinitely many functions, let's take a different approach and average all of these functions together and plot the mean. We can also consider these infinitely many functions to plot standard deviation lines, which show that with high probability for any given x value, f of x is within these lines. Let's also show the hidden f of x function that we are trying to optimize. Clearly, right now, this model is fairly useless. This is because we haven't trained our model on any data points. In Bayesian optimization, training is done with the objective of updating the distribution of functions so that they are more representative of the hidden function. This is done by sampling a point, we'll discuss how to pick which point later, and evaluating f of x. We can then use Bayes' theorem to update the prior to create the posterior. As you can see, our model is already starting to be more helpful. It is telling us that the closer we are to the data point, the more certain we can be about its value, whereas the further away we get, the less we know. This is exactly what we would expect. In Bayesian optimization, we keep repeating this process, evaluating a sampled f of x and using that evaluation to update our posterior. As we continue, this posterior will become much closer to our hidden function. However, how do we know which x to sample? Ideally, we want good exploratory values of x that can give us as much information about our function as possible. But our true aim is to find the highest f of x we can, in which case it might be best to ignore exploratory locations and exploit the information we have already learned. This is where acquisition functions come in. Their role is to deal with this trade-off between exploration and exploitation with an exploration-exploitation parameter xi, and give a score corresponding to how much we want to sample a given x value. Then we sample the x with the highest acquisition function value. So we have simply replaced our maximization problem with another maximization problem, except now it's easier as this acquisition function is quick to calculate. A simple acquisition function would be one that maximizes the expectation of improvement. That is this function, where f of x plus is our best value so far. Once x is fixed, we can use our prior distribution over all functions to get a distribution over f of x like so. It's actually more common to include the exploration-exploitation parameter like so. This lets us control our exploration versus exploitation. When xi is low, we value inputs x with high means, thereby using exploitation, but when xi is high, we value inputs with high variance, thereby using exploration. Now we want to consider all possibilities where f of x is bigger than our best solution so far, and weigh these by how much it improves on our previous maximum. We can represent this with the following integral. And we can remove the maximum like so. We can then use a reparameterization trick by converting this integral into a question about z-scores. This is done by subtracting the mean and dividing by the standard deviation. From this, we can calculate the probability with phi, which denotes the normal distribution's probability density function. Expanding, we get two integrals. We can replace this one with the normal distribution's cumulative probability function. From the other integral, we must evaluate it completely. This gives us a form for calculating our acquisition function. We just need to be careful of dividing by 0 when we implement this. So now that we understand how our acquisition function works, let's show the whole Bayesian optimization process from the beginning. First, we have our prior, we evaluate our acquisition function, and we sample the maximum. Now we update our posterior. We then repeat. We evaluate the acquisition function, sample the maximum, update the posterior. We keep on doing this until we are sufficiently happy with our maximum. But how do we create the distribution over functions? This is done with a model, and the implementations are beyond the scope of this video. But it should be noted that this model can be tuned with hyperparameters that influence what sort of functions are likely to be sampled from their distribution. There are a few things to be aware of. Ideally, we'd have a perfectly calibrated model that creates distributions of functions exactly like we want. The next best thing would be a model that creates distributions of extremely different functions, meaning that we overestimate our uncertainty. In this case, we will likely still find the global maximum. It might just take a few more tries, as we will naturally explore these regions of high variance. The worst thing that we could do is have an overfitted model that underestimates the variance. In this case, we avoid exploring and prematurely converge on a point, possibly a local minimum. This should hopefully make sense. The exploration of an acquisition function is directly influenced by the original function's variance, so if the variance is extremely low, the exploration will be low too. Because of this, it is important to be very careful of any optimization of hyperparameters given to the model, and if you're at risk of overfitting, you should either sample hyperparameters or optimize with heavy regularization. In our example, we just have one dimension, so we shouldn't worry too much about this. However, in problems where we deal with much larger dimensions, we will typically have a small number of data points, as f of x is expensive to evaluate. Because of this, we often find ourselves in a low data regime, where we are more at risk of overfitting. And that's all. Time's running out, so let's get back to mining.